Welcome to EducAgent Studio, where a crew of AI agents help us teach and you learn with ease. Here's the problem we'll solve today. Part A. If A is invertible and AB equals AC, prove that B equals C. Part B. For a specific non-invertible matrix A, find two different matrices B and C with the same left product AB equals AC. We begin with the given equality. Multiplying B and C on the left by the same matrix A produces the same result. The key question is whether that shared left factor can be cancelled. Subtract AC from both sides. Matrix subtraction is valid when sizes match. Now we want to factor out A to compare B and C directly. Use distributivity. AB minus AC equals A times the quantity B minus C. If we can show B minus C equals 0, then we're done. Since A is invertible, we can multiply both sides on the left by A inverse. The inverse cancels. A inverse A equals I, and A inverse 0 equals 0. Because I times the quantity B minus C equals B minus C, we get B minus C equals 0. Invertibility is exactly what guarantees cancellation on the left. Now we use a specific A where cancellation can fail. If AB equals AC, then A times the quantity B minus C equals 0. So we just need a non-zero difference D equals B minus C that lands in the 0 output of A. Matrix multiplication by A acts column by column. AD equals bracket AD1, AD2 dots. So AD equals 0 exactly when each column DJ satisfies ADJ equals 0. This turns the problem into finding a non-zero vector in the null space, then building columns from it. Let's solve for the vectors x that get sent to 0. Multiplying gives the same expression in both rows, x1 plus x2. So the null space is all multiples of the vector 1, -1. The easiest way is to set C to the 0 matrix, then make B non-zero, but annihilated by A. Here, the first column of B is the vector 1, -1, and the second column is 0. Both are in the null space. Clearly, these matrices are different. So if AB equals AC, cancellation must have failed. Multiply. Each row does 1 times 1 plus 1 times -1 equals 0, and the second column stays 0. And of course, multiplying any matrix by the 0 matrix gives 0. So left cancellation fails when A is not invertible. The entire story is about whether A has an inverse. If it does, 0 output forces 0 input. If it doesn't, some non-zero inputs can still map to 0. Invertibility gives true cancellation on the left. The counterexample works because A has a non-trivial null space, so different matrices can collapse to the same product. Stick around. Next up is another neat idea that makes these matrix mysteries feel totally predictable and fun to spot.